Hi guys, welcome back to Calculus. This is Mr. Robeson here. Today we are looking at where functions are increasing and where they're decreasing. We're going to take a look at something called the first derivative test, and then we're going to find intervals where functions are increasing and decreasing. All right, so increasing and decreasing functions. So if we take a look over here, we have a graph of a continuous function. We have a section here where it's decreasing, a section here where it's constant, and a section here where it's increasing. So when we talk about increasing and decreasing, we're always moving from left to right. So we're always like the direction we read. So as we move from left to right, what's happening with the function? All right, so as you can see here, it's going down. And if we looked at the slope of the tangent line here, at each of these points, it would be negative. All right, so what we can say then is that if our derivative is negative for an open interval, then that means the function, the original function, is decreasing. And we can say it on an open interval or on the closed interval. We include endpoints here if we want to. If our slope is 0, like our constant here has a slope of 0, so that means our derivative equals 0 for all x in an interval, then we say our function is constant. It's not increasing or decreasing. And if we look here, our derivative would be positive, our slopes would be going up. So if our derivative is positive for all values in an open interval, then our function is increasing. All right, so that's how we can tell if a function is increasing or decreasing without looking at the graph. We can just take its derivative and look, is it positive? Then the function's increasing. Is it negative? Then the function is decreasing. Is it 0 over an interval? Then it's constant on that interval. All right, so let's take a look at an example of how we would do this. So here's our function, f of x equals x to the third minus 3/2 x squared. We want to know where it's increasing or decreasing. It's asking specifically for open intervals, which is often what the AP exam does. Open just means we'd write them like this. If it said closed intervals, then we could close in the A and the B. Either one's acceptable most of the time on the AP exam. So our steps here to do this, first we want to take the derivative. Then we want to find something called the critical points. We want to know where the derivative could change sign. So where does it equal 0? Where is it undefined? All right, so we take our derivative. We get 3x squared minus 3x. If we brought down the 2, it's going to cancel with that 2. We can factor out a 3x. Factoring is usually pretty useful when we're doing this. All right, so now we set it equal to 0. We don't have anywhere where it's undefined because it's not a fraction. So we're going to get 0 from the first guy, and we're going to get 1 from that guy. All right, now what we want to do is, I like to call it a sign analysis chart, is we take a number line. Here's a number line. On that number line, we put our two x values where it could change, their critical values. So 0 and 1. We put them in order. And then we put all of our factors over here. 3x, x minus 1. So let's see. Now we just look at the sign of 3x. So we pick a number out here like -1. And if we were to plug -1 in here, we'd get a negative number. If we were to plug in a number between 0 and 1 like 1/2, we'd get a positive number. And if we plug in a number out here above 1 like 2, we would also get a positive number. We're just looking for signs here. So if we plug in a number down here like -2, we'd get a negative number. Plug in a number here like 1/2. 1/2 minus 1 is -1/2, so it'd be negative. And then plug in a number out here like 2. 2 minus 1 is positive. Now we can put these signs together, and that'll give us the sign of the derivative, f prime. We can always just multiply signs because these are always just factors, so you can either multiply or divide, but the same rule works for multiplying and dividing signs. So a negative and a negative is a positive and a negative is a negative, a positive and a positive is a positive. And when I say and, I mean multiply. Negative times a negative is a positive. All right, so now we have the signs for our derivative. So that tells us what our function is doing. So back over here, last step. If the derivative is greater than 0, our function is increasing. Derivative less than 0, we're decreasing. So we're positive, that means we're greater than 0, so we're increasing. Negative means we're decreasing. Positive means we are increasing. So that means our function will be increasing from, let's see, -infinity to 0. And again from 1 all the way up, so to positive infinity. And our function will be decreasing just in this middle section from 0 to 1. All right, and we could have done a closed interval here at 0 and closed at 1 and closed at 0 and closed at 1 here. We never do closed on the infinity signs, so we always have open there. All right, so the first derivative test. So let C be a critical number of the function, and let the function be continuous. So continuous is important. So there's not a jump, there's not a vertical asymptote, it's not a hole on the open interval containing C. If f is differentiable on the interval, except for possibly at C, because it could be a corner, that's what this means, could be a corner, then f of C can be classified as follows. So if f prime changes from negative to positive at C, so we've got f prime, we're negative at one side, positive on the other side, that means f would be decreasing and then increasing. So if we go from decreasing to increasing, the function is going to look like that, or maybe it could look like that. But either way, this is going to be a relative minimum at the value there. So this was C. All right, and usually when we say relative minimum, we say a point. So we would plug it in to get C, and we plug it into the original function, we get C, f of C as our point. All right, the same thing happens if we do the other way around now. So here's C, here's f prime. We go from positive to negative, so we're changing signs in the derivative. That means f will go from increasing to decreasing. So it means we're going to go from going up, stop, and go down. Or we're going to go up, stop, and come down like that. Either way, that is a relative maximum. So that is the highest point relative to everybody around it. All right, and if we go from positive to positive, that means our function will go from increasing to increasing. So that means we'd be going up, we'd kind of go flat, and then we keep going up. Or we'd be going up, keep going up, and then keep going up. So this would be vertical, this would be a horizontal tangent, but we can keep going up. Same thing where if it's negative and negative, so again, this is at C, so that means our function will be decreasing and then decreasing some more. So we'd be going down, get flat, and then go down more, or we'd be going down, vertical tangent, and then go down some more. All right. So that's what the first derivative test tells us. It basically looks at does the sign change or does the sign not change, and it tells us what happens at those points when it does or doesn't change. All right, so let's apply the first derivative test here and see if we can find our relative extrema. All right, so first thing we need to do is take our derivative. So we get 1/2 minus cosine of x. Next thing we're going to do is we're going to set that equal to 0. Add the cosine over, we're just going to get that cosine of x equals 1/2. Now we need to know where cosine is 1/2. Well, let's see. All students take calculus. So A and C, quadrant 1, quadrant 4 is where cosine's positive. We're going to have 1, 2. The other side's going to be the square root of 3. So that means this is going to be a 60-degree angle, or this would be pi over 3. This would be 2 pi minus pi over 3, so this would be 5 pi over 3. 6 pi over 3 minus pi over 3. So we get x equals pi over 3 and 5 pi over 3. All right, next, we want to know where is this positive and where is this going to be negative? So we take a look at our sign analysis chart, which isn't always so easy with trig functions, but we'll give it a shot. So we can change signs. Let's see, we're starting at 0, so we have a starting point. So I'm going to start here right at 0, and we have a stopping point here. We're stopping at 2 pi. And let's see, we've got pi over 3, and we've got 2 pi over, no, not 2 pi, 5 pi. 2 can change to a 5, there we go. All right, so if we try somewhere here in the beginning, like near 0, so if I were to plug in 0 into our derivative, which is this guy right here, because that's what I want, the sign of the derivative, cosine of 0 is 1, 1/2 minus 1 would be negative 1/2. So it's going to be negative up here. I know 0 is not quite in that interval, but somewhere close to 0, the same thing would happen. If we plug in something between here, like maybe pi, cosine of pi is negative 1. 1/2 minus negative 1 would be 1/2 plus 1. We'd be positive. And then here again, it's going to go back to being negative. If we plug in a number near 2 pi, it's going to be 1 again. 1/2 minus 1 is going to be negative. So that means our original function will be decreasing, increasing, decreasing. And our original function is continuous. Therefore, this right here will be a minimum and this right here will be a relative maximum. So at x equals pi over 3, we're going to have a relative min, and at x equals 5 pi over 3, we're going to have a relative max. All right, if we want, we can find the point by plugging it in. Sine of pi over 3 is root 3 over 2. So we would get the point is pi over 3 comma, let's see, 1/2 times pi over 3 would be pi over 6 minus square root of 3 over 2. It's not really a nice looking point, but you know, it's a point. And this one would be 5 pi over 3 comma, let's see, if we plugged in 5 pi over 3 here, we would have 5 pi over 6 minus, it's going to be negative, so it's going to be plus square root of 3 over 2. All right, so there are our points. And let's see, yep, there they are. So here's pi over 3 right here. And here's our relative minimum, and here's 5 pi over 3, and there's the relative maximum. Again, we're not looking at the endpoints here, but yep, that would also be the absolute min and the absolute max here. So it's the absolute min and the relative min, and the absolute max and the relative max. So they can both be the same thing, and it happens quite often. All right, let's try another example. So first thing, is this a continuous function? Yeah, it is. So f is continuous. So that means we don't have any problems with the graph. So let's take a look at its derivative. We're going to do a chain rule. So we bring down the 2/3. We've got x squared minus 4 to the 1 less exponent. So it's going to be negative 1/3 times the derivative of the inside, which is 2x. So we're going to get 2x times 2, so 4x on top. We've got a 3 times the 3rd root of x squared minus 4 on the bottom. And there is our derivative. All right, so now we want the critical point. So we set the top equal to 0 and the bottom equal to 0. The top gives us 0. The bottom gives us 2 and negative 2. All right, so now we take a look at our number line chart. So we got to go, well, from negative infinity to positive infinity, but we got negative 2. We've got 0. And then we've got 2 in order. So our factors would be a 4x. And then I'm just going to put the whole bottom. 3 times the 3rd root of x squared minus 4. All right, and let's see what happens with the signs there. 4x is the easy one. It changes at 0. Everything below 0 we plug in there, it's going to be negative. Everything above 0 is going to be positive. With this guy, so if I plug in something out here like negative 3 and square it, that's positive 9. 9 minus 4 is 5. The cube root of 5 is positive. 3 times a positive number is positive. Same thing would happen if I plugged in positive 3. If I plug in something in between negative 2 and 2, like 1, I'm going to get negative under the cube root. The cube root of a negative is negative. 3 times a negative is negative. So the inside's going to be negative. So now if we look at what the function does, a negative and a positive is negative. 2 negatives, positive. 1 negative, negative. 2 positives, positive. If there's an odd number of negative signs, it's going to end up negative, which tells me that our function f of x is decreasing, increasing, decreasing, increasing. So I kind of like to draw like little dots here. It helps me to see if it's a min or a max. So we've got a relative min here at negative 2. We've got a relative max here at 0, and another relative min here at positive 2. And if we look at the graph, we'd have to plug it back into the original. 2 and negative 2 both give us 0. These are both relative mins. They're both also absolute mins. And this guy is a relative max, but depending on the interval you use, it would not be an absolute max. One more example here, then I think we're done. So now we're going back to finding relative extrema, and I think we've got a product rule, or sorry, a quotient rule happening here. We do have an issue with domain. So x cannot equal 0, so it's not continuous there. But we can still use 0 on our number line chart. We just can't have a minimum or a maximum there because we have a vertical asymptote. The vertical asymptote is the equation x equals 0. All right, so we want to find our derivative. So it's low d high minus high d low, square the bottom, and away we go. So x squared squared is x to the 4th. We're going to get, let's see, 4x to the 5th minus 2x to the 5th minus 2x on top. bottom we still have x to the fourth. Let's see, 4 of them minus 2 of them gives us 2x to the fifths minus 2x over x to the fourth. We can factor out that top. We can factor out a 2x, and we are left with x to the fourth minus 1 over x to the fourth. And then one of these x's can cancel and leaves us with x to the third down there. Now we set the top and bottom both equal to 0. All right, if we plug in 1 or negative 1 here, we're going to get 0. So x equals plus or minus 1. On the bottom, we get x equals 0. So those are critical values. They're not critical points, all right? Because 0 on the bottom here, we already said it's a vertical asymptote, so that can't be a point. So now let's look at our number line chart. So here's my number line. I've got to have negative 1, 0, and 1. I'm going to put the whole top together. Sometimes I factor it, sometimes I'll keep it together. It really doesn't matter. It's whatever is easiest for you to do. So there's our factors. X to the third, that's the easy one. It's negative if you plug in a negative number. It's positive if you plug in a positive number. X to the fourth minus 1. So if I plug in a number down here like negative 2, that's going to be positive 4. Or no, positive 16 minus 1 is positive. Times 2 is positive. If I plug in a number in here, like a fraction, we're going to get a negative out of this. 2 times a negative is negative. Same with over here. And if we plug in back 2 again, we're going to get positive again. So that means our functions, sorry, we're using g here. G prime is negative, positive, negative, positive. So that means g is decreasing, increasing, decreasing, increasing. So that means we got a minimum here at negative 1. At 0, we got a vertical asymptote, so don't forget that. And at 1, we're going to have, looks like another minimum. So let's see what the graph looks like. Yep, there it is. And if we plug in those points into the original function up here, that's where we're going to get the 1, 2s and the negative 1, 2s. And they're both relative mins. Probably should have wrote that over here. Relative min, relative min. All right, and we had the vertical asymptote there at 0, and there's our graph. All right, so that's how we find where things are increasing and decreasing. It's also how we find relative mins and maxes with our first derivative test. All right, and we're writing intervals where things are increasing and decreasing. I guess we could have done that a little more. Like we could have written like an interval here that it's increasing from negative 1 to 0 and from 1 to infinity, and it's decreasing here from negative infinity to negative 1 and from 0 to 1. All right, so we can always do that sort of thing too as well. All right, so that's it for this section. Next section, we'll look at concavity, the shape of the graphs.